Thank you for joining us today. I'm Tatiana Palladini and I'm your webinar host. In today's webinar, we will dive into the world of hydrogen, from production to usage, and discover how simulation can enhance every step of the process. And now I'm delighted to introduce our speaker for today, Andrea Lario from our expert partner BSIM Engineering. Andrea Lario is pre-sales engineer at BSIM, specializing in modeling and simulation of complex systems and reduced order models. He's passionate about innovation and cross-fertilization between different industrial fields. Thank you for being here with us today, Andrea, and now the stage is yours.
Okay, thank you, Tatiana, and welcome everybody to this webinar. As Tatiana has already mentioned, today we are going to talk about modeling and simulation for industrial application related to hydrogen technology. And we are going to do that following the agenda that you can now see on your screen. And so first of all, we will start by introducing BSIM, so who we are and what we do. In the second section, we will introduce this concept of system simulation in general and in particular the tool Simcenter Amesim. And in then section number 3, 4, and 5, we will see 3 different applications related to hydrogen technology. In particular, in section number 3, I will present a residential microgrid where hydrogen production is involved. Next, we will consider a case about hydrogen transport. In the end, we will show a case in which we will model a refueling station. So, but first of all, let's introduce BSIM. So BSIM is a Siemens expert partner, and we operate in Austria, in Germany, in Switzerland, and in Italy. And we have 2 main activities. So the first one is that BSIM provides customer with Siemens simulation software, and of course Amesim is one of them, and testing solution as well. And these tools are used for product design, optimization, and validation purposes. Beyond the software distribution activity, we provide support to our customer, we provide training, and also engineering services. In general, the goal of BSIM is to help R&D teams and technical offices to innovate and to design better products. I'd like to mention also the fact that we have a recent addition to the BSIM portfolio, and these are the Siemens machines, which are basically software add-ons that can be installed directly on CNC machine without changing the CNC code, and they allow to optimize the production. But now we can start talking about the main topic of today. So we will introduce system simulation and Simcenter Amesim. So every time we have to design a new product or a new system, some questions like the one I reported on the left-hand side of the slide arise. For example, what is the best architecture for my system? How does my system behave? What's the proper sizing of the components? How do subsystems interact? How can I optimize my system? And so on. The answer to these questions in general are not trivial, since modern products and modern systems are complex. And so system simulation in general can help us in finding answers to these questions. In particular, system simulation is able to provide physical insight on multi-physics systems that we are modeling, considering their dynamic response to some given input or some scenarios. So we basically have seen that system simulation tools are naturally well suited for tasks which one has to perform during the so-called pre-design stage. For example, they help us to sizing our system, to select a proper architecture, optimize our system, and so on. And traditional, let's say, application of system simulation. But nowadays, with the aid of system simulation, we can do much more than that, much more than the pre-design phase. For example, system simulation can be used during the detail design phase. Indeed, the 0D, 1D tools can be used, for example, in cost simulation with high accurate some 3D tools, for example, PM tools and so on. for setting dynamic boundary conditions. Another important application of the system simulation is related to actual commissioning of controllers. So in this case, system simulation tools can be used for creating a digital replica of our plant. And with this digital replica, we can test controllers. Moreover, troubleshooting can also take advantage from system simulation as well. And finally, digital twin. In particular, digital twins are deeply connected to system simulation, and this is a point which I really like to underline, because thanks to the digital twin technologies, system simulation stops supporting just the design phase and influencing the complete life cycle of the product. So basically, this was a short overview on system simulation, but how can we apply system simulation to application related to hydrogen technology? A personal note, I'm aware of the fact that hydrogen-based applications nowadays are still somehow a niche in the industrial framework, but I think it's important to start talking about this topic because it's rapidly gaining traction. So system simulation for hydrogen can give a significant contribution when, for example, production of hydrogen is involved. For example, we will see later a case with microgrid, residential microgrid, can help us also for solving problems related to transportation of hydrogen. And later we will see also a case in which we will see a sketch of a complete refueling station. In this case, hydrogen has to be stored and compressed. So that was an overview on system simulation and on hydrogen application. Now let's start to talk about Simcenter. Basically, the term Simcenter indicates the family of products which Amesim belongs to. Indeed, Simcenter is the Siemens portfolio of simulation software and testing solution of Siemens, which help us to design, simulate, and optimize of the product we are designing. And Amesim, in particular, is the system simulation solution of Simcenter. Today, I don't want to provide a definition of Amesim, but you can easily find one on the internet. And in general, there are different types of simulation, of definition. Some of this definition underlines that Amesim is a tool for system simulation, thus focusing on the final applications. Other definitions instead stress the fact that a 0D, 1D simulation tool, so they tend to underline the physical aspect in Amesim, and other definition instead define Amesim as a DAE solver, therefore stressing the numerical aspect of this tool. All of these definitions are correct, but I think that a good definition should report the feature of Amesim, which I reported in the box on the right-hand side of the slide. First of all, Amesim is able to perform multi-physics simulation. Thus, in the same sketch, we can have components which belongs to different physical domains, electrical, mechanical, fluid, and so on. Second point, Amesim is able to perform and predict dynamic phenomena. So we can use Amesim, for example, when we have to see the response of our system, when I have to switch it on or switch it off, or when I change settings, for example. Another relevant point of Amesim is the off-the-shelf component. In particular, users have a great number of libraries containing validated, calibrated, and ready-to-use components, which were created and tested in an industrial environment. And these greatly contribute to speed up and to simplify the creation of complex systems. Last but not least, Amesim is able to provide a significant amount of information about the system we are designing since the early design stages. So we want to sum up, we can say that Amesim allows the user to virtually assess and optimize the performance of mechatronic systems. Many features and utilities are also implemented in Amesim, and these make the tool powerful and at the same time quite easy to use, and you can find some of them in the list which I reported on the left-hand side of the slide. So, for example, Amesim has an internal optimization tool, and this can be used for finding optimal parameters combination. Then we have also a CAD import feature, which allows to import solid geometry or, for example, piping networks directly in our Amesim model. And this, of course, is useful and it helps to speed up the process of creating models. And then Amesim can exchange data with other tools thanks to dedicated interface, for example, Simulink interface, thanks to the ability to import and export FMUs files, but also thanks to external API. So we can interface, for example, it with Python if we are interested in. And thanks to the creation of a reducer order model, which can then be used by other tools. And so Amesim, it's not just a simulation tool, but it wants to be a simulation platform, open to be interfaced with other tools. But let's go back to the main topic of today's webinar, hydrogen technology. So why should one use Amesim for the simulation of hydrogen-related applications? I think there are different reasons for doing that. The most trivial one is the first one, which Amesim helped me in get physical insight on relevant phenomena which characterize the system without the necessity to build up physical prototype. This is fundamental in a fast-paced environment as the one related to hydrogen technology in order to enter new markets or to maintain a competitive advantage against my competitors. Moreover, SIM can be used in order to the time to market. There are different reasons for that. The first one is that I don't have to basically build physical prototypes, or I reduce the number of physical prototypes that I have to build. And then I can virtually verify complex control strategy, reducing the commissioning phase. Moreover, Amesim can help the user to evaluate the losses and compare different designs, different architectures, in order to limit losses. And this is a very important topic in terms of sustainability. Moreover, we think generally models as perfect product, but with Amesim we can also inject faults or losses in order to evaluate the response of the system to a faulty condition. Finally, we can use models for discovering problems during the operative life of our system and predictive maintenance as well. So this was an introduction about system simulation and about Simcenter. Now we can start to see the first application, which is related to residential microgrid. So in the model, in the sketch of the model, which I'll show you in the next slide, we will find fuel cell and electrolyzers. So Amesim offers the opportunity to model the behavior of the same component with different levels. This capability of Amesim is usually referred as scalability. In this case, for example, we have 3 different models of fuel cell reported on the left-hand side of the slide. The simplest model in this case is the one on the top. And we can see, for example, that with this semi-empirical model, we have the complete polarization curve, but we cannot, for example, keep into account effects related to concentration of oxygen at the cathode side of my fuel cell. While we can keep into account this phenomenon with a more advanced model, which keep into account the electrochemistry of the fuel cell. This is clear from the case on the bottom, where we have a dynamic model of the fuel cell with GDL. So we model also the gas diffusion layers of the fuel cell. In general, what's the best model to be used? In general, among these three cases, in general, the best model does not exist. It depends on the specific application we have to deal with and on the level of maturity of our design. Indeed, more complex models in general require a higher number of parameters, which probably at the early design stage of my system are not available yet. A final note on scalability: the models reported there in this slide can represent either a fuel cell stack or a single fuel cell. Thus, we can have the ability to a detailed model of my stack by connecting together in series or in parallel, for example, multiple fuel cells models. So now we can see the microgrid. So in particular, on the right-hand side, we have a microgrid model, looks like in Amesim, and we can see that we reconstruct the complexity of our system by combining blocks together. Each of these blocks contain a mathematical model which describes the behavior of the component in our system. So in this case, the dynamic electric load is represented by domestic appliances, and the energy absorbed by the load can be taken directly from the solar panel, from the battery, or from depending on specific condition and on the control logic. And we will talk about control logic in the next slide. In the schematic, the solar energy in excess can be used for recharging the battery, or to produce hydrogen with the electrolyzer. The hydrogen produced is then stored in an hydrogen tank. This model can be used, for example, for estimating the production of energy for different irradiation levels, and also to test control strategies. As I mentioned before, in fact, here implemented in our system, we have also implemented a state machine which defines the control logic of our system. So given the state of our system, the instantaneous states of our system, some events are triggered. We can see that two main blocks. The one on the left is referred to a sunny condition, while the other one is referred when there's no sun. And let's start from the block on the left. So when there is sun, the solar energy is used for satisfying the energy request, and the excess is used for recharging the battery. If the battery is full, we use the excessive energy for producing hydrogen thanks to the electrolyzer. If the battery is charged and the tank is full, then energy is just injected into the grid. Probably we sell the energy to the provider. On the other hand, if there is no sun, the power request which we had from home appliances is satisfied by the battery and by the fuel cell, if the battery has a low residual charge. So now we can see some results. So we can see the graph on the top basically represent the consumption and the energy depending on its origin during 24 hours. So the yellow line, it's basically the electric power load due to home appliances, and it's always negative because it's always absorbing energy from our system. And at the beginning of the simulation, we don't have a residual residual energy in our battery, and so the electric energy is fully provided by the fuel cell. Then the solar panel starts to produce energy, and excess in energy produced by solar panel is basically charging my battery. Then when the battery is almost full, it starts to produce hydrogen thanks to the electrolyzer. When the sun goes down, the battery provides the energy to the home appliances up to the end of the simulation. Different months will have different average solar irradiation levels. And so the graph at the bottom shows the different balance in energy between June and December. And as we can expect, for example, the solar energy in June is much more the one we produce in December. So in the end, this model is used for having a better insight on the system and for estimating the various control strategy in order to minimize, for example, the cost of the energy, but also for keeping into account factors which can help to extend the life of the components which we have inside our microgrid. For example, we can see if we are able, if our controller is able to maintain the state of charge of the battery between the 10 and the 90%, because these allow us to extend the life of the battery. And in the previous example, we have seen how to use this related to the generation of hydrogen. And with this case, instead, we will deal with a case for the transport of hydrogen. Okay, to be honest, I quite like this test case because it gives you an idea of the capability of Amesim to capture a complex phenomenon, to describe a complex phenomenon, and does that very simple layout. Indeed, this test case is simply a straight pipe, which is approximately 60 meters long. This pipe connects a cryogenic tank, which should be on the left-hand side of the schematic, to the external environment. In this specific model, we do not consider the cryogenic tank, but Simcenter Amesim library for modeling it, and we can also simulate phenomena related to boil-off and sloshing. Of course, sloshing if your tank is on an aircraft, for example, or on a moving object. This case has the aim to study complex phenomena because when the hydrogen is injected into the pipe, changes of phases occur or does not occur depending on the temperature of the wall of the pipe. At the beginning of the simulation, the temperature of the wall, if I remember correctly, is around 6 Celsius degree, and it's equal to the external, let's say, room temperature. This is a challenging case because one has to deal with change of phases of the hydrogen, which is injected at minus approximately 250 Celsius degree, and with transient thermal phenomena. And we will see a comparison between experimental and the numerical ones obtained with Amesim. So, in order to provide a correct description of this phenomenon, we discretize the pipe with multiple repetition of a basic structure. And this basic structure is reported on the right-hand corner of the slide. And this simple structure is based on 4 components. 2 are referred to the fluid domain, and there's a fluid capacity and a fluid resistance. And 2 instead are referred to the copper wall of the pipe. And the 2 components are a thermal capacity and a thermal resistance. And these 2 domains are connected together thanks to a thermal port. And thanks to this port, they exchange information. In this model, the thermal effects of the air have been considered negligible and therefore omitted, but one can easily also include that effect if he is interested in studying that particular case. So the results obtained thanks to this model reported on this slide. In general, the points represent the experimental results, while the dot lines are the ones obtained with Simcenter Amesim. The plot on the left represents the evolution in time of the temperature in correspondence of 4 different stations. And this station were, of course, the position of the station were chosen accordingly to the experiment which were performed. And in general, there is a good agreement between the data obtained with the simulation and the data and the experimental data. Simcenter Amesim can be also used for investigating effects related, for example, to geometric tolerances And so we want to investigate, for example, how geometric tolerance influences the behavior of our system. If we consider, in this case, we considered a change in the inner diameter of plus minus 1, and its effects we can see that are relevant, and the term transient is applied, and the effect is shown on the plot on the right-hand side. So this is basically an example on how Amesim can be used for obtaining additional insight with respect to a given baseline configuration. But we can also think to test different strategies. For example, we could consider a pre-cooling of the pipe in order to shorten the thermal transient and to partially avoid change of phase of H2 inside the duct. Okay, that was the second case. The third case instead is a little more complex application, and it's related to a refueling station. So, as we have seen at the beginning of the presentation, Simcenter Amesim can be used for finding answers to questions in the box on the left-hand side of the slide. So, again, what's the best architecture for my system? How can I optimize my control? What's the maximum flow or pressure inside my system, and so on. In the Amesim sketch on the left, we can see that in this case, many different domains are involved, because we have compressor, which mainly mechanical components. Then we have pneumatic lines for transferring hydrogen between the different sections of my system. We have heat exchanger in order to keep under control the temperature inside my system, and so on. Basically, the hydrogen is entering my system from the left-hand side of the sketch, then is compressed, then stored in tanks. And these tanks are at a different pressure. So we have a low pressure tanks, a medium pressure tanks, and a high pressure tank. And then on the right, we have the tank, the vehicle tank, which we have to fill in. Thanks to Simcenter Amesim, we can evaluate the pressure and the other relevant characteristic of our fluid in different points of our system. And for example, we want also to check the refueling time, and we want, for example, to keep this refueling time under 5 minutes. So on the right-hand side of the slide, we have some plots with some results, the most relevant one, the ones on the top. And in particular, the graph on the left is representing the various pressure I have inside all the tanks during the refueling operation. In red, there's the pressure inside the vehicle tank. In green, the high pressure tank. In blue, the low pressure inside the low pressure tank. So you can see that actually the vehicle tank is completely filled in less than 5 minutes, but then we require something like other 5 to 6 minutes, more or less, in order to recover the initial values of pressure inside the tanks of the refueling station. Indicates that the high pressure tank is the one which is lower in covering the initial level of pressure. So in the top right corner instead, we have the instantaneous mechanical power demanded by our compressor for compressing the gas. And this slide is about the compressor. In fact, thanks to Amesim, we have the opportunity to create detailed models of the compressor. And in particular, in sketch, you can see at the bottom of the slides, there are 4 double effects compressor. In particular, the compressor chambers and the pistons are modeled with the aid pneumatic component design library, which allow us to create detailed model of valves, actuators, and the compressor, of course, keeping into account the dynamic and the inertia and the geometry of the single components. So we do not just have a simple functional representation of the phenomenon, but we have a detailed representation. So the compressor, then the chamber and the pistons are connected to a drivetrain, which are the components in green at the bottom. And these components and the parameters of these components are chosen in order to match the stiffness, the damping factor, and the geometry of the real drivetrain. This drivetrain is then attached to a reductor and to an electric motor, which is presented in the box and the violet components in the sketch. So this model is able to give information about the entire drivetrain in terms of torsional and vibration. And, for example, we can study the effects of different valves, different values of inertia in the angular acceleration. But if we want, we can also study the lubrication system as well. So in this case, in this example, basically 2D and 3D models were used for reconstructing the behavior and the geometry of a piston, and this was coupled with the lubrication system. And models like the one which I represented on the slide are very useful because they help us to evaluate the pressure which is acting on the bearing ring and the oil film thickness accordingly to the load of the rotating shaft. So we have seen detailed model of compressor, we have seen the lubrication system, but in the same sketch we have also a control system. And again, here we define a state machine in order to control our system, and that one we have seen already in the first case I showed of the microgrid. What I wanted to show in particular in this case is Simcenter Amesim. We can produce a model to be used as a virtual plant for the commissioning of the controller, allowing us to virtually test them. So in this case, for example, as it is shown in the figure, the state machine is placed by one implemented in a controller, in a virtual controller, and the user can directly interact with this virtual plant through an HMI. The Automation Connect tool was used for allowing data exchange between the virtual PLC and the Amesim plant model. So all the main phases which are commonly employed for developing controllers basically can take advantage of a virtual plant. And so we can use a virtual plant during the modeling the loop phase, during the software in the loop phase, and also during the hardware in the loop phase. So this was my last slide, and I wanted simply to underline how Simcenter Amesim is able to support not only the design phase of a multi-physics system, but the entire product development process. Next, there will be a Q&A section, and I've already seen that there are some questions in the chat. Okay, so which kind of optimization is performed in the example? Is it given an objective function and constraints, or just a list of what-if scenarios? Okay, basically there are two ways in Simcenter Amesim, just to sum up a little bit, to define control strategy. One is thanks to a state machine, and it's the cases I can also have PID, for example, controllers, which are not state-based, but they are based on a continuous control. So these are two different control strategies, and in general, signal library, in which I can define signals, and that's sort of Simulink logic. I can define some signal, I can elaborate signals, and I can define there, for example, a PID controller. Here they are talking also about optimization. In that case, it's a little different question, because the state machine is not really for optimization, but for control logic. While for optimization, there are a couple of different optimization algorithms which implemented in Amesim that, for example, can be used for finding optimal parameters combination in order to reach a given goal. Is there any practical application for the test case I showed, number 2, about the transport? And yes, the idea is that, again, it's a sort of refueling station, also the second case related to hydrogen transport, because in that case, for example, in aerospace industry, it's very common that I have cryogenic, basically, tanks, and therefore I need some refueling station which can take advantage of a simulation as the one I showed during the second test case, so the one with the simple pipe, straight pipe with hydrogen injector. There's another question, it's do you consider hydrogen as ideal gas or real gas? Okay, this is in general not specific to hydrogen, but in general to fluid and gas, how they are treated in Amesim. Okay, actually I can do both. There are simple cases in which maybe an ideal gas approximation is enough for me, and I'm free to use that. But then, if I want, I can also have a more advanced gas model, for example, and so I can choose the best model I want for modeling my gas. For example, there's one of the most used real gas model, the one based on the formulation of Peng-Robertson. And so we are running out of time. So we will come back with other answers to your question eventually after the webinar. And I want to thank everybody for taking part to this webinar, for the answer you gave me during the polls. And so I want to thank you, everybody, and thank you, and have a nice day.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.